what we're doing here is we're going back to the old, all the different properties again. And I know that this was one section that not everybody really liked a whole lot. And when we had all of our exponent rules. So we had, when you're dealing with exponents, if you had the same base and you were multiplying them, you would just add your exponents. You had the idea of power to a power, you would multiply them. You had basically like a distributive property of an exponent. We had negative exponents, which just meant they weren't happy where they were, so you just put them and you change their size. Same deal if it was in the denominator to start with, it moved up to the numerator. When we had division, remember what we said? We said play war. And I know that the actual technical way of saying it is just take the top and subtract the bottom. But if you do that, sometimes you might have the negative exponent, which means you have to flip it again anyway. So I always do the idea of play war. So whoever's got a larger exponent wins, and then everything moves to that side. You'll see this as we go along. And then obviously the last one was the distributive property with division. And the last one, it's not on there. What's anything to the zero power? So what we're doing today is we're going to work with these same exponent rules that we've had, but we're going to have them with rational expressions, with rational exponents, which means we'll have fractional exponents. So everything works the same. You just deal with a fraction. And that's where things just get kind of muddy, especially if you're one of those types of people that don't like to use extra space on paper, or you use slashy fractions. So this is going to kind of pull the Band-Aid off, if you will, on the slashy fraction and the saving of space. So let's look at a few examples. And then we got a whole bunch of this stuff to go through today. So if I have 3 to the half times 3 to the 3 halves, do they have the same base? They do. So what do I do to the exponents? I add them. What's 1 half? What's 3 halves? 4 halves, which is yeah. You have, think of it this way, you have to worry about if this was just values of x. And it would just be that. And since it's numerical, they're putting it at the end. Same deal goes for power to power. When I have, and I apologize that they use slashy fractions, I think it's awful. When we have power to power here, I have 4 to the 3 halves squared. So when you have power to power, you have to multiply those. So I would get 3 halves times 2, which is 6 halves, otherwise known as 3. So you get 4 cubed, which is 64. Very good. Good enthusiasm. 9 times 4 to the half power. There's actually a couple of ways to do this one. If you go via your order of operations, what would you do first? Multiply them together, you get 36. And what's the half power stand for again? Square root. So what's the square root of 36? 6. That's one way of going about it. It works nicely when they're both perfect squares. Sometimes they're not. Sometimes you have to do some simplification. But in this case, if you go the long way, it's just 9 to the half, 4 to the half. Oops. Good save. which gives you 3 times 2, otherwise known as 6. It still works. It still works. Don't be scared. Here, you know what? Come up here and you show that negative who's boss. You can show the negative who's boss. Say, screw you, Mr. Negative. I'm a positive person. And I'm going to not be afraid of you anymore. I'm going to take my life back from you, Mr. Negative. You on that one? I don't know. I don't know what to do. Don't be afraid of the negative.
You can do that.
What do we do with the negative one?
Oh, you're afraid.
Yes.
This isn't Price is Right where you can yell to the crowd for help.
Okay.
$1! $1!
There's no more.
Becky, are you no longer afraid of the negatives? I know it was a little hesitant for a minute. I mean, I hate to put you on the spot, but it was just kind of perfect time. I mean, at least you wouldn't have to dance. Seven Mondays left, spring break.
14 Mondays.
So 6 to the 5 halves over 6 to the half. So who wins the game of war? 5 halves or 1 half? So what's 5 halves minus 1 half? Otherwise known as 2. Nope. If you want to treat them, if you want to think in your mind that they're just variable x, and then do some everything else. And then last but not least, I don't know, something just showed up. 8 over 27 all to the 1/3 power. When you raise something to the 1/3 power, that means you're taking the what of it? The cube root. Good. Since it's a fraction and it's all being raised to the 1/3, it means I have to take the cube root of both the numerator and the denominator. So what's the cube root of 8? What's the cube root of 27? Otherwise, so your fraction becomes it's math magic. Yeah, these exponent rules today we're not going to see any real equation stuff with it. We'll use these exponent rules again when we get back to the more complex equation. I gave you guys a couple of them yesterday, just a little snippet, but we get to crazy ones later. So we just kind of go back and forth through all of it. Do I need to do all of here? Just do these 2. Actually, do these 3. Take a minute, do those 3, please. So here's a little trick. On that first one, we have 7 over 7 to the 1/3. They both have the same base. They're both base. They always have their base is 7. But we have to figure out who has the larger exponent. Now, the 7 in the numerator doesn't have an exponent, or does it? It's a 1, but I don't write it as 1. I'm going to write it as 3/3. By doing that, you automatically set yourself up for your common denominators, and you can make it work. So you wind up with 7 to the 2/3, go on your merry way. You just leave. So this one you get 1 over 2 to the 4th times 3 to the 4th to the 4th. And then what do I do with that 1/4 exponent? Distribute in, so what's 1/4 of 4? Okay, 1/4 of 4. So you get 1 over 2 times 3, which is 6. Tra-la-la. Yes, I know you can push buttons all day long to get your answers, but would I allow you to do such a thing? So, yeah, right. Do you know the way? Wait, isn't there? Do you know the? No, isn't there a way to the ginger man? Do you know the man to the ginger man? Because there's one way. Oh, yeah, Muffin Man. Do you know the Muffin? I'm thinking that from Shrek. All right, what do you do first here? What is it? You simplify in there. You can. This one you can simplify. Now, what I want you to think of it this way. Think of it this way. This is 12. I can break the 12 apart. Excuse me. I can rewrite that as the cube root of 12 over the cube root of 4. Now, when you dealt with square roots, remember how you're able to break them apart and you can use multiplication and put them back together? It works the same way with cube roots and the other nth root. So this is the same thing as the cube root of 4 times the cube root of 3 divided by the cube root of 4. Now, obviously, this is all still squared, so what simplifies? 4s. You see that? No. Feel better about that?
Yeah.
So now I wind up with, let me move this up, I have the cube root of 3 squared. Now, how would I rewrite that then as a fractional exponent? 3 to the 2/3, very good. Every once in a while, you'll see a division problem like that where you can simplify out, 4s and 3s and stuff. It happens pretty regularly. It's nothing too crazy. It's just one of those rules that works because it follows the same way that you did when you guys worked with square roots. Speaking of, look what I just did. Just a reminder. Just a reminder, just like I said, when you have radicals, you can split them apart and rewrite them as products of two numbers. Same thing with division. You can write it as the quotient of 2. It's a little trick that we get to do from time to time. And I will remind you that every once in a while, we're going to have to rationalize the denominator. Because just like we did last year, when you had right triangle trig, remember how you guys did not like having radicals in the denominator? You want to like root 3 or 2 root 3 over 3, stuff like that. Same basic principle here. We're going to keep all the radicals out of the denominator. We want to have no radicals, no fractional exponents in the denominator. It's a super easy thing to fix, especially with nth roots. I don't know if we'll get to that part today. Might wait for that for tomorrow because it does get a little messy. All right, does this vaguely ring a bell? What's that? It's leaving it. It's not simplified then because it's not an exact answer. And I know that when you get further on, they kind of tend to say that. But most Algebra 2 pre-calc stuff always rationalize the denominator. They turn it into a rational problem then. Excuse me. But I know that when you get to certain levers goes to, you start pulling switches and stuff. When you get to certain levels of calculus, the whole idea of simplifying denominators just kind of goes out the window. There's no reason to at that point because you'll have the CAS version of calculation that does it automatically. All your stuff. So I know after a while you don't have to, but every standardized test, I think every single textbook that I've ever seen when you deal with radicals always simplify denominators. Just one little. I don't need to do these two, do I? So here goes the idea again, kind of a reminder of how do you write radicals in simplified form. Because the computer didn't let me make a nice radical root there. Bless you. We all know how to do the square root of 12. Square roots are pretty easy. We've done those without too much of a hassle. Square root of 12 simplifies out to being what? 2 root 3, very good. When I get to the cube root of something, that means I'm looking for a perfect cube. Now, when you're looking for a perfect cube, you're looking at, well, your list is, well, if you have 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125. So right away, it goes up super fast. You know, if you really start thinking about it. So if you're looking for a perfect cube that goes into 54, it's either going to have to be an 8 or a 27. It's 27, isn't it? 27 times what? 2. So you can split this apart to becoming the cube root of 27 times the cube root of 2. So what is the cube root of 27? 3. So your answer would be 3 cube root 2. Okay. Not too bad? All right. Now, let's kind of show you a little trick here. Before we get to that, when you had this, how did you simplify that to get the radical out of the denominator? Multiply, bless you, multiply by what? Root 3 over 3. Root 3, excuse me. What's root 3 divided by root 3? 1. You multiplied by some factor of 1, didn't you? Now, if you think about this in terms of what your exponents and stuff are, does it change anything if I rewrite it like this? So if I multiply it by 3 to the 1/2, 3 to the 1/2, what you did is that you took the same base and you multiplied it by a number of a fraction to add it up to equal 1. Because your square root was a half power. So by using the property of multiplication, same base, different exponents, you add them together, 1/2 plus 1 plus what equals 1? Well, 1/2 plus 1/2. That's how your exponents became the first power. And this was 3 to the half. And we just wrote it as root 3 over 3. Okay. The only thing that changes when you get to the nth roots is that you have to figure out, well, how do I go from, move this up just a bit, let this right. If I say that this is 3 to the 1/5, 4 to the 1/5, how many more fifths do I need in the bottom? 4. So I would multiply it by 4 to the 4/5, 4 to the 4/5. Do you see that? By doing it that way, by switching out of nth roots to the fractional value, it's so much cleaner to see how much more you have to add up to equal 1. In all honesty, you've been doing it all along. You've just been doing 1/2 plus 1/2. Here you have, in this case, 1/5. I have to add 4/5. So my denominator here becomes 4. My numerator was 3 to the 1/5 times 4 to the 4/5. If I say to put that back into nth root form, it would just look like, what's that? The 5th root of 3 times the 5th root of 4, 20 to the 4th, all over 4. But usually, when you're rationalizing, I'm pretty sure we usually keep our exponents as fractions just because it's that one less step then. But what you're doing is you're just creating pairs of 1 in the denominator. You're still multiplying by 4 to the 4/5 divided by 4 to the 4/5, which is just 1. You're just multiplying by some weird shape of 1 to use the conversions of your exponent rules. Does that make sense? It just looks really, really weird, but it's just adding. We can probably try this real quick. So if you take a guess what you have to be able to have in order to add and subtract radicals and roots. You'd have to have something in common, wouldn't it? Wouldn't that be the same rule if this was 7x plus 2x? Could I add those two together? If it was 7x plus 2x squared, could I add those two together? No. So does that change anything here? No. So when you go through this, you're still combining like terms. So I have 7 times the quantity 6 to the 1/5 plus 2 times quantity 6 to the 1/5. What do you think you get? You get 9. 4. Depending on how we want you to answer it out, as nth root or exponent. Okay? And the other one's very similar, but what do you have to do first? No, you're right, you're right, you're right. What is it? You're right. Uh-huh. If I take the cube root of 16, what do I get? 2 cube root 2. You were on the right track. Because remember, this has an 8 and a 2, and I can take the cube root of 8. The cube root of 8 is 2. So this can simplify first to the 2 cube root of 2. And if I subtract 1 cube root of 2, what's 2 cube root 2 minus 1 cube root 2? 1 cube root 2. Because as soon as your nth roots are identical, treat it just like you would a variable. Okay? Treat it just like you would a variable, and you wouldn't have any issues. Eh? I think after this it goes to variables then. I don't know. Yeah. That just gets messy. All right, we'll stop with numerical here. So let me see what we got. Yeah, we should be able to do that. Let's see.